Okay, so in this case we have a 0.1 kilogram block. It is ball of clay. It hits a 2 kilogram block with a spring in between. Some values are given, and we want to figure out some things about compression of the spring and the like. So initially, if you read this for a second, we know we're trying to find the energy stored in the spring at maximum compression when this ball hits this 2 kilogram block. So we know the distance is 0.4 meters. We know the spring constant of 200 meters, newtons per meter. And then we know that the energy in a spring is 1/2 kx squared, which means that it is 1/2 times 200 newtons per meter times 0.4 meters squared, which yields 0.16 meters squared times 100 newtons per meter, and we are left with 16 Newton meters, which equals 16 joules, which is the energy stored in the spring. Now, it's pretty important to figure out the total speed of this block, because we see situations like this in real life where you throw clay at blocks, perhaps in a ceramic studio. So in this case, we know that we are looking for the speed of the clay block system. So looking for the speed of the clay block system, well, we could think of momentum, but it turns out we're not given a specific value for v, so that's going to be a little tricky. What we have to do instead is notice that we have an energy value, and that energy value is stored in the spring. So the total energy of block and clay has to equal the amount that ends up getting stored, potential energy in the spring. Well, the total energy in this case before the collision would end up being the kinetic energy of the system. So if we think about kinetic energy, it's 1/2 of the total mass times the velocity squared, and that would equal my spring energy. So let's think about what this would entail. Well, if I plug the values into here, I get 1/2 times 2.1 times v squared equals 16. And if you resolve this, you should get 3.9 meters per second. This is in joules, this is in kg, and then you should be able to get 2 meters per second from this. Okay, so let's move on to calculate the initial speed of the block, of the clay. Well, this is where conservation momentum comes into play. Calculating the initial speed, let's give ourselves some space here. Calculating the initial speed of the clay is going to require that, well, we know the speed of the combined system after the fact. If we consider that we have an inelastic collision, well, we know that we have some combined mass times a final speed, and that's equal to the individual masses times the initial speeds. Well, we know that this is, let's undo that. We know that this is 0 because the clay block, or the block that the clay hits, is not initially moving. And we know that this is at 0.1, 100 grams, times V. And the V is the part that we want to know. And we know that's equal to 2.1 kilograms times the VF, which is 3.9 meters per second. And if we plug in the values here, we will know that we get 81.9 meters per second as a final result. That is the V value, which is the initial value of the clay. Okay, so this is dealing with conservation of momentum before a collision, and after a collision. So in general involved with collisions. And so now we want to know that we have a second experiment. An identical ball of clay is thrown at another identical 2 kilogram block, but this time the stop is removed so that the 8 kilogram block is free to move. So in this idea, we have a clay ball thrown at a 2 kilogram block with a spring attached to an 8 kilogram block. This is still going with V, still 0.1 kilograms. And when this hits, this will hit the initial block, which will compress the spring, which will eventually compress this 8 kilogram block, which then will proceed to move forward way after the fact. And that's the situation that we're considering now. This stop that was on this end has been removed. So we want to state whether the maximum compression of the spring will be greater than, equal to, or less than 0.4 meters. And explain briefly. Well, here's the question. Is all of this energy that's stored up in here going to compress this spring before this stops moving? Or at the point where this stops moving and this doesn't start moving? Is there some lag between when this gets compressed all the way to 0.4 and when this starts to move? Well, there shouldn't be. In fact, it's a continuum where there's still going to be some motion, and this energy is not going to transfer initially. So we're going to say that the compression is less because this is still moving at the time that this starts to move. As soon as force is exerted on this spring, well, that compression means that there has to be a force exerted that way on this object, even before this reaches 0.4. And because that's the case, this is going to start moving, which means it's going to carry away some of that kinetic energy. If it carries away some of that kinetic energy, then the spring can never hold the full 16 newtons, or 16 newton meters of energy, 16 joules of energy. So we have a distribution which sees that we have some energy here. Let's look at it in a different color. Some energy here. Some energy in the spring. And then some energy here. And it can't all be, there's no way for it to all be concentrated in this spring at once. There's some motion that way, there's some motion this way, and that's because there is an initial force here. Now, if there were friction on this 8 kilogram block, it is presumable that if the maximum static friction were equal to the force exerted at maximum compression here, then this would have to compress all the way before we would even see motion here. And that's an interesting problem to try out mathematically. So let's state the principles that can be used to calculate the velocity of the 8 kilogram block at the instant that the spring regains its original length. So write the appropriate equation and show numerical substitutions, but don't actually plug anything in. So the things that we have to pay attention to, as this is sort of an interesting problem here, we would have to consider conservation of momentum, and we'd also have to consider a conservation of energy. So in this case, we have the sum of the masses beforehand, this idea that we had some momentum going in, and that would be the 2 plus 0.1 times the v going in, which is 3.9. We calculated this at the top up here. So that's the speed that we have after the collision, the initial collision, and that's the momentum we have going into the initial collision, and that's going to equal, at the end, the momentum of the individual pieces going apart. So we have the M1, or the M of the block and clay, times a V1, and then we'll add that to the mass of the 8 kilogram block times our V2. So if this is V out, and this is V1, this is V2, or this could be V1, V2, and V3, but we have this system of conservation where the momentum going in has to equal the momentum split up amongst the clay block system and the big block system. And then we have this statement of conservation of energy, where we look at the kinetic energy going in, which is the only energy that we have, which is 1/2 2.1 times 3.9 squared, which we know is 16 joules. And that 16 joules has to be maintained throughout the entire collision. And so if there's nowhere else for it to hide, well, we can have a look and see that it is equal to the energy going out, whatever the speed of this part is after the collision, plus whatever the speed of this part is after the collision. In essence, we're looking at what we see to be an elastic collision, because we're stating that we have a conservation of kinetic energy here. So if we look at this, we see 2.1 times V1 squared, whatever the speed is here, and then that is going to be added to 1/2 times 8 times the V2 squared, whatever the speed is here. So having two equations, simultaneous equations, a system of equations, we can solve for the missing two values, V1 and V2, if we solve them as a system. So you don't have to solve them as a system. According to this, do not solve for velocity, but you do want to solve them you do want to set up the equations here. Okay, that is it for this problem. We'll move on to another in a different video.